Okay, let's get started. Anybody else need to turn in their take-home quiz? Now's the time. You still trying to copy stuff over? Why don't you do it at the end? I'll let you do it. Here, turn in what you have now.
You want me to just give it to you and then I'll...
Yeah, I'll give it back to you. Anyone else? Anyone else? Oh, okay. Okay, thank you. All right, thank you. Thank you. All right, is that it? Okay, so we are going to continue in 8.1. I did some notes for you that I've handed out. Hopefully you have those in front of you. Some of what is on this we already talked about last time. Some of it is new. So we kind of ended class last time talking about the limit of a sequence. So we spent some time last time saying, hey, look, here's a list of numbers. You try and come up with a formula for it, right? Yeah, that's what we did. I gave you a list and we tried to come up with formulas. And we saw that we'd have to mess around with things and try and see, how much, maybe it jumps by 2 every time, or maybe it's a power of something. Well, now what we want to know is if you have a list of numbers, are those numbers headed to something? Right? Is it headed to an actual number, getting closer and closer to something? So we have this idea of the limit. So we say that a sequence has the limit L, and this is what we'll write. And this should look familiar to you, right? We've seen this notation before, except that we're going to let n go to infinity. Now, n, remember, is the number, n represents where we are in the list. So like a sub 1 is the first number, right? A sub 2 is the second, then the third, then the fourth. So if we're going to let n go to infinity, it's like we're looking all the way down that list, right? Where's that list headed? If we say it's going to be equal to L, this is another notation we use for it, then what it means is that we can make our sequence a sub n as close as we want to L by taking n to be sufficiently large. So if we go far enough out into the sequence, we will be as close as we possibly want to L. Now, a picture of what's happening here is, well, I have it down here, I think, don't I? There we go. Okay, so look, let's ignore the red for now, okay? Let's say that we're saying that this sequence of black dots approaches L, all right, or goes to L. What we're saying is that, okay, the distance between the first point and L is pretty big, right? But as we go down, it's getting closer and closer and closer. And we can get it as close as we ever want to L by going far enough out. It's kind of, visually, I think it's pretty easy to see, right, the idea? All right. So some more terminology here. We did talk about this. If the limit exists, then we say that the sequence converges or is a convergent sequence. Otherwise, we say that the sequence diverges or is divergent. Right? So those are our terms. And we've heard those before with improper integrals. But now we get our first theorem. And this theorem is going to be really helpful for us. This theorem says that if we take the limit as x goes to infinity, so notice we're using x, not n, right? If we take the limit as x goes to infinity of some function of x, if that happens to be L, and then we define a sub n to be f of n, that means we restrict the function to the natural numbers, then the sequence, the limit of the sequence must also be L. So that may be confusing to read, but all it's saying is this. Let's say that we have a function, good old function that we've dealt with our whole life, this red curve right here, right? Let's say that that function is headed to L. Then the sequence if we created a sequence that was just that function restricted to the natural numbers, we would get all the dots on that curve, right? So wherever the red curve goes, our dots have to go. Do you agree with that? Okay. That is how we're going to get around doing problems where it's hard to figure out what the sequence is doing. We're actually going to be able to use L'Hopital's rule because of this. All right? So let's actually do one. I'm ready to do an example here. If you came in late, you need to turn in your take home right up here. Thank you. So let's take a look at this sequence. Does a sub n equal n squared over 4n squared plus 1 converge? If so, what? That's not what. What does it converge to? All right, so when we're looking at a sequence and we're asking whether or not it converges, what we have to do is take the limit as n goes to infinity of the sequence. Right, so that's what I'm going to start with. I'm going to take the limit as n goes to infinity of n squared over 4n squared plus 1. Now, let's just think about what happens here. As n gets bigger, okay, don't worry. As n gets bigger, the numerator would get larger, right, and head off to infinity. And the denominator would also get large and head off to infinity. So back in Cal 1, we would have something that looks like infinity over infinity. And what we did with that was L'Hopital's rule, right? Okay. We cannot use L'Hopital's rule because of what I tried to explain last time, that when you have a bunch of dots, you can't talk about derivatives. However, the theorem that we just looked at, right, said that if we consider a function of x where we basically are taking the entire sequence here and replacing everything with x, then that's a nice function that we would have seen maybe in Cal 1, right? And now we ask ourselves, what's the limit of this function as x goes to infinity? And you would say, infinity over infinity, right? So then you would use L'Hopital's rule. So I use an L on top. So L'Hopital's rule tells us we can do what? If we have infinity over infinity, derivative of the top and bottom separately, right? So what's the derivative of the top? 2x, derivative of the bottom, 8x. And their x's cancel, don't they? And you're just left with 2 over 8, which is 1/4. So if we graph this function, which is, this function, if we graph it, is a curve that we would not pick up our pencil, right? We just draw it. This function, as we go to infinity, is headed to 1/4. So if we go back and look at the sequence, which is just a bunch of dots on that curve, then that should also go the same thing, right? So this should go to 1/4 by the theorem. The theorem provides us that result, all right? So for the first few problems that I do, anytime I want to use L'Hopital's rule, I'm actually going to convert the sequence to a function of x, do L'Hopital's rule, and then use that answer back here. But later on, I won't do this, and I would just say, yeah, we know we could do L'Hopital's rule, and then that would just be like 2n over 8n, and then it would cancel, we get 1/4. So I will kind of skip this step, because it'll take a little more time, but I want us to understand that we're not technically doing L'Hopital's rule on a sequence. That's not possible. We're doing L'Hopital's rule on the function and then using the theorem to get the result for the sequence. All right? Okay, that pretty straightforward? Okay, let's do another one. Same question. Does this converge? Yes or no? Sine of n over 1 plus the square root of n. So the first thing we do is we write down the limit. This is what we're looking for, the limit as n goes to infinity of sine of n over 1 plus root n. So what's happening here? if n starts getting big, what is sine of n going to be doing? So sine of x, right, would be a smooth curve doing this, right? Sine of n is a bunch of dots. In fact, let's look at it real quick. I just want to make sure we understand what that sequence would look like. So let me just put in here sine of n. Why is this? Oh, there we go. That's sine of x, right? Sine of n are just these dots. And let me move out here. Why is that not doing that? I'm going to put a bunch of them. There we go. Those are kind of too big now. Okay, so if we could take the red curve out, which I don't know why I don't take that red curve out because it's kind of in our way. But do you see that the dots don't really look like this? They just almost look like just scattered everywhere, right? But they're just because they're falling at random places on the sine curve, right? So sine is going to go up and then down. But, you know, look at this right here. We got this up here, the next point's here. So it is on the curve, right? But it doesn't give us that shape the way the red does, right? Make sense? So we know that the top is just scattering all over the place. It is between -1 and 1 though, right? And then the denominator is getting huge, isn't it? Okay, so can we use L'Hopital's rule on this? What do you need to have to use L'Hopital's rule? Infinity over infinity or 0 over 0. I don't have either one, right? The bottom's headed to infinity. The top is not headed to 0, and the top is not headed to infinity, right? It's kind of scattered around. So no L'Hopital's rule allowed here. Can't use it. So we have the next theorem. Which is called the squeeze theorem. And maybe you've seen this before in Cal 1 also. I'm just barely going to be able to squeeze it, but you have that. So here's what the squeeze theorem says. The squeeze theorem says, let's say we have 3 sequences, all right? 3 sequences, where we have a sequence A sub n, a different sequence B sub n, and a last sequence C sub n. But this is that they follow that string of inequalities. So the sequence A sub n, if you were to plot this sequence, it is always below or equal to, so when you graph it, like the y coordinate, so to speak, is always smaller than or equal to the other sequence, and that sequence is always smaller than or equal to this sequence, then if that's true, then if the limit of the 2 outer sequences, if these two right here head to something, right? If they both go to L, then the middle sequence must also go to L. So here's C sub n, right? That's C sub n. Do you agree that that C sub n is always bigger than always above or equal to all the red ones, right? So the red ones are the B sub n. And then the A sub n, do you agree that these are all below the red ones? Okay? So if I know that the top sequence heads to L, and the bottom sequence heads to L, and the middle sequence is always between the two, then that sequence must also go to L, right? So that's what the squeeze theorem is doing. You're pinching your sequence in between 2 other sequences. The key is that you have to know where these 2 sequences go, all right? If you don't know where these go, then that doesn't help. They both need to go to the same thing too. So I'm actually going to use that theorem here to do this problem. So right now I'm kind of stuck. So here's what I'm going to do. I'm going to try and come up with an A sub n, which is less than or equal to a B sub n, which is less than or equal to a C sub n. Did anybody notice in the notes that I wrote n bigger than capital N sub 0, n naught? Did anyone notice that? And no one really asked me about what that means, so I'm going to point that out right now. What this is saying is that when you look at the picture, I said that this C had to be above the B and the B had to be above the A, right? That's what I said? This little condition right here says that it doesn't always have to be that way. Like, they can be in a different order, okay? Like the red ones could be up here and the black ones down here. But at some point, okay, at some point, and not, from that point on, as long as from that point on they maintain this, C on top, B in the middle, A on the bottom, as long as from that point forever it maintains that inequality, then this is going to hold. All right? So it doesn't have to always maintain this, just at some point and then from there on. Does that kind of make sense? In the picture I put up here for y'all, in the picture I put up here for you, it's always true. From the beginning to the end, it's true. This one's on top of the red one, which is on top of this black one. But it doesn't always have to. So you could have like all sorts of different scattering. Does that kind of make sense? Okay. All right, so here we go. I'm gonna start off. Well, the thing that I really want to squeeze down is the sequence that I don't know what it does. Okay, so I don't know what this sequence does. I think I know what it does, but that's the one that I want to pinch in between two sequences. All right. So now it's my task, your task, to come up with two sequences that you can guarantee me this one has to be less than this one, and this one has to be less than this one, and that one has to be less than this one. So we need to come up with these, and we need that these two sequences, we know what their limits are, and that they go to the same place. Oh, okay, that's pretty simple, right? Do y'all understand what we're trying to do? Like, we have to come up with something? So here's the way I'm going to do it. I'm going to do some scratch work on the side here. I know that sine of n, this is about all I know right now, okay? I know that, no, that's not true. That's what I meant to say. Do you all agree? That's true. Yeah. All right, so I'm doing some scratch work over here. I'm thinking to myself, I need to come up with these, right? Okay, so I know that this inequality is true just because I took pre-cal, right? Then I say to myself, all right, well, I also know that I can always take inequalities and I can divide by numbers. I can divide by things, right? And the only thing I have to be careful about is when you divide an inequality, if you divide by a negative number, the inequality flips. Do you remember that? Okay, but I'm going to divide by something very clever here. I'm going to divide by 1 plus root n. Now, why am I going to do that? Well, because it matches what I'm trying to squeeze, right? And I almost have a squeeze going on here. If I divide that by this, I have to divide this one by that, right? And I have to divide this one by that. Now, do I have to worry about flipping these inequalities? Why not? These have to be positive numbers, right? N, remember what n starts at 1, right? 1, 2, 3, 4. So that's always positive. I'm adding 1 to it, so that is positive guaranteed. So dividing by that number doesn't flip my inequalities. So do you see that I have almost like naturally created this and this, like the two I was looking for, just by looking at the original statement about sine of n. Now, we have to hope that we can figure out what these go to. So do we know what those go to as n goes to infinity? 0, right? Look at this one right here. This one right here, if this one's 1, right? And the bottom is going to become huge. A fixed number over something that becomes huge goes to 0, right? So we know this goes to 0 if I take the limit. And we know this one right here will go to, well, negative 1 over infinity also goes to 0, doesn't it? And so do you see that I've squeezed this thing down in between two things that go to 0? Which means that this must also go to 0, right? Okay, so I'm going to write this down. Now that I've done all that scratch work on the side, I'm going to say, okay, this is less or equal to that. Negative 1 over 1 plus square root of n. And then now what I'm going to do is I'm going to take the limit as n goes to infinity of negative 1 over 1 plus root n. That must be less than or equal to the limit as n goes to infinity of sine n over 1 plus root n. And that must be less than or equal to limit as n goes to infinity of 1 over 1 plus root n. So this was me just writing down the statement that we all agree is true, and then me taking the limit of each of them. And now let's just evaluate the limit. So we already said that this is 0, right? That must be less than or equal to this limit, which I'm trying to find. But that must be less than or equal to 0, because that's 0. So the only number between 0 and 0 is 0, right? The only thing you could possibly squeeze in between 0 and 0 is 0. So that has to be 0. So this limit is 0 using the squeeze theorem. What do y'all think of that? All right, moving along. Next theorem. There's a theorem here that has to do with the absolute value of the sequence. Did y'all see that? This theorem says if the limit as n goes to infinity of the absolute value of a sequence goes to 0, then the limit of the sequence without the absolute value also goes to 0. Let's do an example. What is the limit? Yeah, let's do this one. I'm just going to write it as a limit. What's the limit as n goes to infinity of -1 to the n over n squared? All right, so this sequence is what kind of sequence? Forget the limit. What kind of sequence is that? Because we have the -1 to the n. We call that a what? Alternating sequence. This is an alternating sequence, right? So if we plug in 1, we would get a negative number, right? Plug in 2, we get a positive number, so on and so forth. So this thing keeps flipping back and forth between positive and negative numbers. If we were to graph it, -1 raised to the n over n squared. Yeah. I need to zoom in on that. Maybe not go out so far. A little further than that. Yeah, you can kind of see it. Yeah. So it's like you start out with a negative, then a positive, then a negative, positive, negative, positive. And you can see where it's headed, right? You can see it's headed to 0. But the way we need to do it, the way we need to verify that, is by using that theorem. So let's take a look at the limit as n goes to infinity of the absolute value of this sequence. So when I take the absolute value, does that -1 to the n matter anymore? Whatever this turns out to be up here, it's either going to be 1 or -1, right? And when I take the absolute value, it's just going to be 1. So this is equivalent to the limit as n goes to infinity of just 1 over n squared, right? And we don't need the absolute value on the bottom because n is already being squared, so we know it's positive. And that limit you can do just by looking, right? It's fixed over infinity. That's going to go to 0, right? So that goes to 0. So the theorem says if the limit of the absolute value of the sequence, so this right here is a sub n, right? If the absolute value of the sequence, if that limit goes to 0, then what can we say about the original one? This goes to 0 also, okay? And we're done. Now, be careful. What is the limit as n goes to infinity of -1 to the n? So let's say we're getting a little bit kind of haphazard and we're not paying too close attention to what that theorem is saying. And we say, okay, I'm going to use that theorem. And I say, all right, limit n goes to infinity. I take the absolute value of this, right? But then if I do that, I get limit as n goes to infinity of what? Of 1, right? Now, that means your sequence is just 1, 1, 1, 1, 1, 1 the whole time, right? Which converges to what? 1, right? It's always 1, yes? So your answer is 1 here. With me? Now, does that mean that this is 1? Why not? That's right. The theorem says if the absolute value of the sequence goes to 0, the answer is 0. But if it goes to something else, the theorem, you just throw it out the door, okay? You can't use it, okay? Understand? So you have to be careful with this theorem. It only works when the absolute value of the sequence goes to 0, all right? So this basically tells us nothing. And then, well, let's answer the question. I mean, let's write out that sequence. If a sub n equals, what is the sequence here? Negative 1, 1, negative 1, 1, negative 1, 1. What does that converge to, or does it converge? It doesn't converge, right? It's kind of like the sign without all the crap in the middle, right? It's just 1, negative 1, or sorry, it's the other way around. Negative 1, 1, negative 1, 1, negative 1, 1. That never goes to anything, right? You can't say 1 because it jumps to negative 1. You can't say negative 1 because it jumps to 1. So this would diverge. Which one? You could use the squeeze theorem if you could figure out what to squeeze it between. And you're never going to find any two functions to squeeze it between that both go to the same place. You won't be able to. So the squeeze theorem works only when you can come up with those functions. Like if I come up in here and I just do negative 1 raised to the n, right? Where are they? There they are. Let me bring them in like this. My computer is smarter than we are. It actually is having it converge to something. E to the 2i. What? Okay, don't worry about it. Don't worry about it. So look at what's, you're asking about the squeeze theorem, right? So you would have to come up with a sequence, one sequence that always stays above this one, right? And then one of them that tries to go below this one. And yes, you may be able to get two sequences that converge to something, but they're not going to converge to the same thing. This one can't go below that, right? And this one can't go above that. So there's no way these two will ever go the same place. So no squeezing. Now, can you squeeze it in between like a funnel? Like, not a funnel, but a region? Yeah. But that doesn't tell you where it goes. All you can say is, well, if it converges, it's somewhere in there. Yeah. Okay. Y'all okay with this? All right. Just making sure I'm getting through the examples I want. Okay, next thing on the notes has to do with something I believe I did talk about last time, and that is a special sequence. A very special one that's going to pop its head up a few times, and that's any sequence, a sub n, that looks like r to the n. Here, r is a number. R is just a real number. Okay? So if our sequence is some number raised to the power n, then look at what this theorem says. The sequence r raised to the n converges to 0, right? That's what this says. If what? The absolute value of r is less than 1. So as long as the absolute value of r is less than 1, it's going to converge to 0. So if I ask you right now, does pi to the n converge, what would you tell me? No, right? Because pi is bigger than 1, right? So pi to the n is not going to converge to 0, so this is going to diverge. All right? I should probably have said that. Let me put that on here. Let's add that on here. If the absolute value of r is bigger than 1, it will diverge. And there's one more case that we're not covering here. We know that the absolute value of r is less than 1. I told you it's going to converge. If it's bigger than 1, it's going to diverge. I mean, think about what's happening here. Pi, look at what the sequence looks like. Pi, pi squared, pi cubed, pi to the 4th, right? Just that thing's blowing up, isn't it? Okay. But what about if r is, what if r is 1, though? So we know what happens if it's less, absolute value is less than 1, absolute value is bigger than 1, but what if r is 1? That would be, your sequence would be 1, 1, 1, 1, 1, 1, right? Because 1 to any power is 1. So that'd be 1, 1, 1. So what would that converge to? Then the sequence 1 to the n converges to 1, right? That would be a very special case. We're not going to see that, but, well, I think we will see 1 to the n. We're just going to say that's 1. But so when you're looking at a number to a power and you're asking about the convergence or divergence of that sequence, all you have to check is whether or not the number down here is bigger or smaller than 1. All right? All right. And we don't need to talk about why that's true, or are you comfortable with the idea that each, if this was smaller than 1, that each time you raise it to a power, it gets smaller and smaller and smaller and smaller? 1/2, 1/4, 1/8, 1/16, so it gets small. Okay. All right.
You mean a fraction, not a negative number, right? So is that why you say absolute value? Because a negative number will still converge if it's...
As long as the absolute value of it is less than 1. So if you looked at this sequence right here, -2/3 to the nth power, and you say, does that converge? You'd say yes. Converges because the absolute value of this is less than 1. Yeah. All right. Let's try this one. I'm going to define a sequence for you now. Let's talk about its convergence or divergence. How about 2 to the n plus 3 over 5 to the n? Yeah, what's that? How about that? What do you think there? So what's happening with this sequence? If n starts getting big, what does the numerator do? Gets big, right? Denominator gets big. You do have infinity over infinity here, don't you? Which means you could use L'Hopital's rule if we change these to functions of x. But then you have to be taking derivatives of exponential functions, right? You'd have to take derivative of 2 to the x plus 3 and 5 to the x. And the derivatives of exponential functions get a little messy because you get natural logs in there. You remember, like, derivative of a to the x? Derivative of a to the x? What's a derivative of a to the x? Itself, natural log a. So you could do that, but it's going to start getting messy with logs, right? So what I'm going to do is instead of that, I'm going to rewrite this and get used to this. If this is like mind-blowing to you what I'm doing right here, just get used to that. I mean, we're going to do a lot of that right there coming as we continue through the next few weeks. All I did was use properties of exponents, right? That's what that really means. Now, watch what that allows me to do. These are both raised to the n power, aren't they now? So I could rewrite this as 2/5 to the n times 8. Would you agree? So my sequence, 2 to the n plus 3 over 5n, is equivalent to the sequence 2/5 to the n times 8. Now, if I were to start letting n get big, right, and take the limit here, this is r to the n, right? And that 2/5, the absolute value of that is less than 1. And so we know that this is going to go to 0, right? And times 8 still goes to 0. So I know that this sequence right here, watch the way I say this, converges with the arrow, means converges to 0. All right? But I had to like peel that thing apart a little bit, didn't I? How about this one?
Will always go to 0, sir?
Well, what?
It will always go to 0?
What? Sorry. What do you mean, will it always go to 0?
You said, I'm assuming from after n goes to infinity, right? There.
It only goes to 0 because this right here is my r, and that r is less than 1. I'm using the theorem. Yep, I'm using the theorem. And if if the absolute value of that is less than 1, right, then that goes to 0. And that's just 8, and 8 times 0 is still 0, right? All right, what about this one? What does this do? So I'm asking, does this converge or diverge? All right? So does this converge or does it diverge? I'm going to start writing C and D like that, okay, because I don't like to write it over and over. Does it converge or diverge? Well, we have to take a limit, right? Now, I didn't do the limit here, did I? I just kind of rewrote it. And I said, I already know what that does, right? If I took the limit of this, this would go to 0. So I put the arrow to represent that's what would happen if I took the limit. Okay, now this one I'm going to write the limit out. N is going to go to infinity, square root of 4n plus 1 over 7n plus 3. Now this problem, although it, well, let's see. What would you do here? I mean, what are you thinking? Say again? Okay. Now, this is an expression, so we can't just like arbitrarily square it. We can't just square it out of nowhere. As n goes to infinity, can we just look in here and see what happens right here? That becomes infinite, right? And this becomes infinite. So we get like a little infinity over infinity. The question is, can you, when you take a limit, can you actually just do the limit inside the root like that? You know what I'm saying? Like, are you allowed to really be looking inside the function? Because that's a root outside. And the answer is yes. All right, that's why I'm giving you this example. When you have composition of functions like this, you can pass the limit into the composition. So I'm allowed to take the limit in here. Now the limit in here is infinity over infinity, and if I did L'Hopital's rule on that, I could, right? So I'd have to change this piece right here, and I have to take that and write that as a function of x. And then 7x plus 3, then say L'Hopital's rule would give me, limit, sorry. This was supposed to be limit. X goes to infinity. So I'm taking that, I'm rewriting it as a function of x and taking the limit as x goes to infinity, and then doing L'Hopital, and that just gives me 4/7, right? So if the function does this, the sequence does it also, right? So this limit will be what? The square root of 4/7, right? Okay. The only tricky part, or there's really not a tricky part, this is just to illustrate to you, like I said, are you allowed to pass a limit through a function like that and do what's on inside here separately, and then pull that answer back in here, and the answer is yes, all right? So long as this function is continuous, and that's pretty much all we're going to deal with in this class, so there's not a whole lot to worry about there. We doing all right? Now for something more interesting. Our test is, is it a week from today? It's a week from today? I'm thinking this is going to be the last section on the test. Today's material will be the last section on the test, but I will continue to lecture. All right? So 8.2 won't be on the test, but that doesn't mean turn me off. Okay, because you'll need 8.2 for sure. Unless we do 8.2 and you like it, and then you're like, yeah, put that on the test then. All right, so how about this one? You ready saying no? Five n factorial over 5n plus 2 factorial. And before I do this, I want to ask y'all a question about this. Is there a difference between 5n factorial versus 5n in parentheses factorial? Is there a difference between those two statements? Okay, so let's see what would happen if we plug 1 in here, right? This would really mean 5 times 1 factorial, right? Well, we would figure out what 1 factorial is, right? What's 1 factorial? It's just 1, right? So this would just be 5, wouldn't it? What happens if we plug 1 in here? You get 5, but then factorial. So this is 5 factorial, which is really 5 times 4 times 3 times 2 times 1. These are not the same thing, right? So a set of parentheses around this is not just for fun. These are completely different expressions. See the difference? Okay. So I have 5n factorial on top, 5n plus 2 factorial on the bottom. I would like to know whether or not this thing converges or diverges. One thing we can do that I should point out, this is a major revelation here, is that L'Hopital's rule is off the table because factorial functions are not defined on, you know how we can take some sequences, turn them into functions, and then do our L'Hopital, and then go back? You can't turn this into a smooth function because factorial is only defined at the integers. All right? Now I'm going to put an asterisk next to that because actually factorial is defined. There is another version of it that you can define it everywhere, but that not here. Okay? Not here. So no L'Hopital. It's infinity over infinity, right? Yeah. Do y'all understand it's infinity over infinity? Like this is going to get huge. That's over something that's huge. So any ideas on what we might be able to do here? Cancel? How? That's how we're going to do it, but how do you cancel?
Just expand it out.
Okay, so let's expand it out. 5n factorial really means 5n times what? 5n, but then take 1 away. So 5n minus 1. And then times 5n minus 2, right? And then 5n minus 3 and 5n minus 4, right? And we're going to continue this. Dot, 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 times, dot, and then until we get down to 1, wherever that is, down the line, right? Now, what about this one right here on the bottom? This is going to be 5n plus 2, right, which is the first one, and then 5n plus 1, right, because you're taking 1 away. And then you keep going. 5n, and then 5n minus 1, and you'd keep going, right? 5n minus 2, and you'd keep going all the way till you get down to 1. And yeah, I heard it, but you saw that right there, right? See, starting at this position right here, all these start to cancel. All the way down to you get your 1s, right? So the only thing left is you've canceled everything up top, so you have a 1 up there. And then down here you have 5n plus 2, and then 5n plus 1, right? We have done no calculus. This is just algebraic manipulation of the expression, right? So a sub n is that, right? That's a simplified version of that sequence. Now, let n go to infinity. You just get 0, right? So if we take the limit of this and let n go to infinity, we have a fixed number on top, and the number on the bottom is blowing up. So this thing converges to 0. Make sense? Now I'm going to redo it because if I were doing this problem, I would do it a little different. I would have said 5n factorial on top. I wouldn't have touched that one. Then I would have done 5n plus 2, 5n plus 1, right? And then I'm supposed to do 5n and then keep going, but the rest of it is 5n factorial, right? Like from here on, that's 5n factorial. So I say 5n plus 2, 5n plus 1, then the rest 5n factorial. That cancels with that, and we're done. Do y'all see that? You just have to remember that that factorial means that this thing carries on, keeps going, right? All right. How about this one? How about n factorial versus, or over, n to the n? L'Hopital's off the table, right? As soon as you see a factorial, L'Hopital's off the table. So that means we better be able to algebraically figure it out, right? We better be able to algebraically figure out what's going on. And the only other thing we have is the squeeze. That's it. That's all we've got. We can do a limit. If we can turn it into a function of x, we've got L'Hopital. If we can't, then we've got to somehow algebraically manipulate it, hope for the best, or try and squeeze it down between two things. So, any suggestions here? Pardon me?
It is possible with what you've shown us.
Yes. This is going to be possible. How about we write out what it means? Can we start with that? Just start writing out what it means. All right, so what does n factorial mean up there? N times n minus 1 times n minus 2. We don't know how big n is, right? But we're assuming that this thing goes down until we get to 1, right? Like that? All right. That's the top. What's the bottom? What would 3 to the 3rd power be? What would 8 to the 8th power be? What would 10 to the 10th power be? What is that? What's n to the nth power? What does it mean? If I say take n and raise it to the n, what are you going to do? Multiply n times n times n times n. How many times? N times. So isn't the bottom n times n times n times n times all the way down to the very last one, which is n? Agreed? This should be dot, dot, dot there. Yes? Yeah. So how many factors are in the numerator? How many factors? We have 1, 2, 3. To how many factors would that be? If we have 4 factorial, and I rewrite that as 4 times 3 times 2 times 1, how many factors are here? 4, right? 8 factorial is 8 factors, right? There are 9 factors on the top, right? How many? 9. There are n factors on the top, right? How many factors are on the bottom? n. So they line up on top of one another, don't they, perfectly?
Yeah.
Like this over this, the next one over the next one, and every one of these I could kind of group up as their own thing, right? Y'all are with me on that? Okay. Now, I'm going to squeeze it now. You ready? Here it comes. Now, I put equals here, but let's get rid of that equals. I don't want to write all that again. I'm going to squeeze this. I'd like to try and squeeze this between two things that I know go to the same place. So I start to recognize something. This right here, this first thing, whatever it is always going to be 1, isn't it? No matter what n is, that's always going to be 1. Times. Now, let's look at the second one here. What can you tell me about that one? If I take n minus 1 and divide it by n, what can you tell me about that number? It's less than 1. Do you agree? That number is less than 1. No matter what n is, well, n has to be positive, has to be from the natural numbers, but so long as this is a natural number, whatever I plug in here, 5, this would be like 4 over 5, right? That's always going to be smaller than 1. So do you agree that this expression is 1, this expression is smaller than 1, right? So if I put another 1 here, this would be true. 1 times 1 is bigger than or equal to these two multiplied. And then the next one would also be what? Smaller than 1, smaller than 1, smaller than 1. So let's see, 1, I have another 1. And I would have, how many 1s here would I have? N 1s, right? Agreed? But, this last one, this last one right here, I'm not going to put 1. I'm going to put 1 over n. Okay, so let's see if you believe that. We know this one is 1, right?
Yeah.
The next one's less than 1, less than 1, less than 1, all the way down till I get to here, right? And then the next one I just say is equal to that. So is this still true? Is this bigger than or equal to that? Yes? And where does this go? If I let n go to infinity here, where does this side go? It goes 0, right? Now, this side. What can you tell me about this side? This whole thing has got to be bigger than or equal to what? What am I trying to squeeze it between? We know that one's going to 0, right? Well, this one also has to, I could just put 0 here. Why can I put 0? Why can I put 0 here? These are all positive numbers, right? n over n is positive. n minus 1 over n is positive. These are all positive numbers, right? So this has got to be bigger than or equal to 0. So I've kind of come up with a very clever way of squeezing that thing down between two things. So now what I would have to do, technically, I would have to take the limit as n goes to infinity of this one. The limit as n goes to infinity of this is less than the limit as n goes to infinity of this expression right here.
So how do you know they are positive? It's n.
And what is n? When we're talking about sequences, what is n? Where does n live? The natural numbers. Remember, we said last time, we talked about this double struck n, right? We said that's the list of numbers 1, 2, 3, 4, right? Forever. And so when we were talking about our sequence a sub n, we were always saying that n was going to be a positive integer, right?
Yeah.
So we know that that's positive, positive. We know, well, are you concerned that this might be negative?
Yeah, because if that was 1, and then you subtract 2.
Okay, I like that. If what was 1?
If n was 1.
If n was 1, though, this would just be 1 factorial, right? So I would actually be there. If n was 2, right, then it would just be those two. If n was 3, then it would just be those, right? Like there's no way, this is just n times n minus 1. When I write that, n factorial is n times n minus 1 times n minus 2. When I write that down, we are always assuming that our n is bigger than how far we're going to go down. Does that make sense or not? If it doesn't, look, like right here, this 4 factorial, you see this? I took one away, right? I took one away. I took one away. took one away, and I stopped when I get to where? Here, right? I don't keep taking one away, right? I don't keep going. And that's what would happen here. Like if n was 1, right? You go 1, and then you would stop. If n is 2, you would go 2, and then you go 1, and then you would stop. So these are never going to be negative in a factorial. Does that make sense? We know that the whole top right here is positive. We can just do it that way. The whole top is positive, agreed? Because it's factorial of some integer. And the bottom is n to the nth power, which is positive. So that's definitely got to be positive, and that's bigger than or equal to 0. Squeeze down to 0, squeeze down to 0. That means the middle one has to go to 0. All right. So this converges to 0. All right, let's move on to the next set of notes here. I want to do another one. What? That sequence, n factorial over n to the n converges to 0. I want to do another one. I'm thinking of this one. I'm wondering if I don't even know if we can do this, okay? I'm just curious if we can figure out what n factorial squared over n squared factorial, if we can figure out what that does. I don't think we'll be able to do this. But I want to make sure we understand the difference between those two. So let's write out what the top one is. So that would be n times n minus 1 times n minus 2, all the way down until we get to 1, right? But then all of that squared. Yes? Over. Now the bottom one, we're doing the squared on the n first, right? So what would the first piece of the factorial be? N squared. And then what would the second piece be? N squared minus 1. And then the next one would be n squared minus 2. And then you keep doing that all the way till you get down to 1. Do y'all see the difference between those two expressions? Here you're taking the factorial of n and then squaring it. Here you're squaring the n and then factorial of that. Now I can do something up top. On the top, can I do n squared, n minus 1 squared, n minus 2 squared? Am I allowed to do that? Yeah, because multiplication between each of the factors means you can pass the power through to each factor. So that's legitimate. But then the bottom, n squared minus 1, n squared minus 2, n squared minus 3, and then that's going to go all the way down until I get to 1, right? Yeah, I didn't think we'd be able to do this. Yeah, the problem is I don't see an easy relationship here. Like I know that this is 1, right? You know that's 1? And I know that, each factor lines up one on top of the other. But can you say for sure how big that is? Like on the last one, we were able to say that's less than 1. Is that one less than 1? How would you convince yourself? Is n minus 1 squared over n squared minus 1, is that less than 1?